Hi everyone, welcome to the fourth part of this tutorial on non-convex optimization for high-dimensional signal estimation, spectral and iterative methods. In this part, we'll be talking about how to design non-trivial extensions of non-convex optimization methods so that they become robust to corruptions and yield conditioning, particularly in problems such as low-rank matrix estimation. So let's examine the idea of having the algorithm to be robust to yield conditioning. Just to recall the standard low-rank matrix sensing problem, we are given some matrix of dimension n1 by n2, whose rank is R, that is much smaller than the ambient dimension of this matrix. And in typical sensing problems, we're going to take implicit measurements of this high-dimensional matrix M, which is modeled by some linear operator A. And we'll be collecting a vector of measurements Y, which has a dimension M. Typically, it's going to be much smaller than the ambient dimension of the matrix M, which is n1 by n2, but maybe just barely larger than the degrees of freedom of this matrix, so that we still have some hope to recover this low-rank matrix by capitalizing on the low-rank structure. One particular paradigm we've been discussing in this tutorial is to take this factorization approach by rewriting this matrix M as a product of two matrix factors, X and Y. And the goal is then to find these low-rank matrix factors so that the observation will be approximately matched with what we will think we will measure using this imaging device over this matrix factorization model. All right. So one of the particularly successful paradigm, as also has been highlighted in the previous parts of this tutorial, is using this idea of gradient descent coupled with a clever initialization using the spectral method. Particularly when the low-rank matrix is asymmetric, people usually actually will result to this regularized loss function, which not only has this a standard least square term that measures the discrepancy between the observation and the postulated measurements, but also having this actual balancing regularization, which roughly tries to enforce the gradient of the factor X to be the same as the gradient of the factor Y. Okay, so with this in place, we can still result to the usual standard two-step approach, where in the first step, we'll result to the spectral method to generate a initialization based on the top singular vectors of the matrix A join Y. And once we have this nice initialization, which upon some nice conditions of the measurement operator that will land into a local neighborhood of the ground truth, we can then start to do sort of the standard gradient iterations, just where we simply update the factor matrices along the descent directions of the gradients of the regularized loss function. Okay, so this paradigm has been well studied in the last couple of years in the literature. And one particular result for this approach is given in the following theorem. So suppose our goal is to measure this low rank matrix M that is exactly rank R and has a condition number which is defined as the ratio of the largest non-zero singular value and the smallest non-zero singular value. Then for this particular low-rank matrix sensing problem, where the sensing operator follows the so-called IID Gaussian design, we know using this vanilla gradient descent when coupled with spectral initialization will achieve epsilon accuracy in estimating this low-rank matrix within a number of order of kappa times log 1 epsilon iteration. So this algorithm actually converges in the so-called linear rate, where the iteration complexity only depends logarithmically with respect to the accuracy we would like to achieve. And all this nice computational guarantee will kick in as long as the sample complexity is a little bit larger than the degrees of freedom in this problem, roughly on the order n times r squared times kappa squared. Okay, so similar results has also been obtained for many other low-rank problems, some you already seen in the previous parts of the tutorial, such as for the phase retrieval problem, matrix completion problem, and so Despite this nice result for this vanilla gradient descent, in this part of the tutorial, our goal is try to go one step further by examining the convergence guarantee when the underlying low rank matrix is EU conditioned. Particularly, consider this example where your goal is to recover some low rank matrix in this matrix completion example. And we're just going to look at the convergence rate of solving this problem as a function of the condition number of the underlying low rank matrix. So in this figure, we show that the convergence rate actually degenerates quite significantly as we increase the condition number from the perfect conditioning of kappa equals 1 to just a mild condition number around 20. And we see indeed, this also agrees with our theory such that the vanilla gradient descent converges in a number of iterations that scales linearly with respect to the condition number kappa. Okay, so what this means is if we are dealing with some U condition matrix, then using this vanilla gradient descent approach actually will converge very slowly. Okay, so natural question is, can we actually design a better algorithm that is independent, whose convergence rate is independent with a condition number, so that we can actually probably accelerate the convergence of vanilla gradient descent? As this important assumption premise that we are not going to increase much about the per iteration complexity of this algorithm. Okay, so before I go to the actual algorithm design, let's just think a little bit why condition number could be potentially a big deal in our application of interest. I'm not going to be able to exhaust all the possible scenarios where condition number potentially be large, but let's just think about a sort of a very typical data application where on this slide, we are looking at a particular data set, which is measuring the coloring concentration level at 120 junctions over 180 time slots. So essentially, this gives us a small data matrix with size 120 and times 180. And this matrix is quite typical, where if you plot a spectrum with the singular values, you see the spectrum actually decays pretty fast following this so-called power law spectrum. So what this means is that this matrix indeed can be well approximated by a low rank matrix. So indeed, if we want to approximate this matrix using a rank 5 approximation, which contains about 88% of the total energy of this data matrix, we actually end up with a rank 5 matrix, which has a condition number about 20. Okay? If we want to contain a little bit more energy by using a rank 10 matrix low rank approximation, we see the condition number becomes even larger, around the order of 60. All right. So this indeed highlights the issue that the condition number can potentially be really huge and become non-negligible. Okay, so with this in mind, let's now look at how to actually get to an algorithm design which can actually be robust to the yield conditioning of this matrix. Okay, so with this, we want to introduce this new algorithm called scaled gradient descent. So this algorithm actually, on the high level, is very similar to the previous one that has been introduced, but with two important changes. Okay, so first of all, we're not actually going to change how we're going to initialize the algorithm. It is still going to be initialized using the same methods, such as the spectral method, so that we can find the initial point in this sort of so-called basin of attraction. Okay, what we are going to change is how we are going to perform the local search. Particularly, it turns out we don't even need the balancing regularization as well. We can directly just use the loss function that only contains the least square term of the measurement residue. And in addition, the most significant bit of change is that we're not just going to merely search along the direction of this negative gradient, but rather we're going to apply a preconditioning to this search direction, where we're going to precondition the search direction of the left matrix factor X by a preconditioner that look like Y transpose Y inverse. Okay, and we are going to do the similar thing for the right matrix factor Y by preconditioning its such direction by the inverse of the matrix X transpose X, which is constructed using the left matrix. Okay, so the first important thing to notice is that you can think of this scale gradient descent algorithm as a precondition gradient method, but it's applied to a loss function that does not include the balancing regularization. So no balancing regularization is actually necessary for the success of this scale gradient descent algorithm, both in theory and in application. Second, the construction of these preconditioners only requires you to compute the inverse of a small matrix of size R by R, where R is the rank of the matrix. So if the rank of the matrix is much smaller than the ambient dimension, then computing the inverse of this small matrix is actually going to be much smaller than the complexity of computing the gradient, which scales with respect to the dimension or the ambient dimension. Therefore, by converting the search direction to using the scale gradient, we actually only occur a minimum overhead compared to the method we used earlier for the vanilla gradient descent case. Okay. So with this algorithm in mind, let's just first look at how it actually behaves in practice. So to run this algorithm just on top of the same matrix completion example before, we see that indeed the performance of the scale gradient descent algorithm is indeed quite independent with respect to the underlying condition number, where all the curves essentially overlay on top of each other. So this really highlights the fact that this algorithm achieves a rate that is condition number independent. What is more interesting is that it seems the convergence of this algorithm also perfectly match the convergence rate of vanilla gradient descent when you have perfect conditioning. Okay, so what this really is saying is we can potentially achieve a huge computational saving by running the scale gradient descent algorithm because it converges in a kappa independent manner with a minimum overhead that is on top of the computational complexity of gradient descent per iteration. Okay, so with this encouraging empirical results in mind, let's look a little bit closer at the underlying mathematics for this new algorithm and try to reason about why it can achieve such nice robustness guarantees with respect to EU conditioning. So one of the important observation is that it turns out the update rule of scale gradient descent is inherently deeply connected to running matrix optimization, low rank matrix optimization on top of low rank matrix manifold, which has been studied in a previous literature on coming up low rank matrix optimization algorithm for this type of problems. And particularly, if you think about the updates of this matrix factorization algorithms as sketching out a trajectory on the low rank matrix manifold, for every pair of factorization, it essentially mapped to a low rank matrix, say MT equals XT YT transpose. So from iteration to iteration, you are essentially jumping from a low rank matrix to another low rank matrix. Now, a natural question is that because this matrix factorization is actually not uniquely identifiable with respect to the underlying factorization model, so it's only identifiable up to invertible transforms. So you can get to another factorization without changing the low rank matrix. Now, what is remarkable about scale gradient descent is that the trajectory you obtain on the matrix manifold is actually invariant with respect to which factorization you are taking. So if you take a different parameterization, effectively your next iterate will also go through the same parameterization, and therefore the trajectory of the algorithm is invariant to the invertible transform for this particular parameterization. Okay. Now, This does not necessarily quite explain why the algorithm achieve a condition number independent rate. In order to justify it theoretically, a very important thing is to realize or to sort of identify a new distance metric as a Lyapunov function so that we can track the trajectory of the algorithm very carefully. So one of the candidate for analyzing the distance is actually this new one that is different from the previous analysis of vanilla gradient descent, where we need to properly introduce the impact of preconditioning in the measurement, in measuring these distances. Okay. And coupled with this new distance metric and a more careful trajectory analysis, in one of this year's paper, we come up with this new theoretical guarantee for the scale gradient descent algorithm. In particularly, for the same low-rank matrix sensing problem with IID Gaussian design, we see that scale gradient descent, when using the same spectral initialization, also achieve epsilon accuracy, but within only a number of log 1 or epsilon iterations, where this iteration complexity is provably independent with respect to the condition number, as long as the sample complexity is larger than this order, which turns out to be the same as the sample complexity required by the 2AL algorithm using vanilla gradient descent. So putting together, this is saying, indeed, scale gradient descent actually provably accelerates the convergence of vanilla gradient descent without incurring a higher sample complexity. Okay, so if you're going to use vanilla gradient descent for the low rank matrix sensing problem, now you can safely switch to scaled gradient descent because it basically gives strictly a better convergence guarantee compared to the vanilla gradient descent algorithm. Okay, now so far the theory I have discussed is only for the noise-free case. I would like to talk a little bit about the numerical stability using an empirical example. So particularly, we're going to take this chlorine concentration levels data set that I showed you earlier and look at how the performance, the reconstruction error, scales as a function of iteration complexity for a sort of a typical matrix sensing problem. Now, the high-level message is that scale gradient descent is going to converge much faster than vanilla gradient descent if you are given a small number of iterations. Say around 400 iterations, the convergence, the relative error of scale gradient descent is already much smaller than the error of vanilla gradient descent. Now, if you give this algorithm a significant higher number of iterations, the final performance, the final relative error of vanilla gradient descent will actually match the error of scale gradient descent. So in other words, both of the algorithms will actually converge to the same solution. However, scale gradient descent will converge to that solution at a much faster rate than vanilla gradient descent. Okay, so with that, I would like to now switch to another consideration about robustness, which is about robustness to outliers and corruptions for this type of matrix sensing problems. So in this new model, which we call the outlier corrupted low rank matrix sensing model, everything is pretty much the same, except that when we collect our measurements, due to maybe sensor failures or malicious attacks, a small portion of our measurements may become adversarially corrupted. So particularly, we now have this updated observation model where our observation is written as our typical nominal observation plus an outlier term, where this outlier can have arbitrary entries in terms of magnitudes, except that the number of non-zeros, the number of outliers we have is going to be small. So the cardinality of this vector, outlier vector, is going to be upper bounded by alpha times m, where m is our total number of measurements, and alpha is some number between 0 and 1, which is a fraction of outliers. So typically, you may think about the fraction of outlier alpha as say something as 5%. Okay, now before we try to design new algorithms, let's just do a little bit thought experiment to look at why our existing approaches might fail when we have outliers. So recall that our standard strategy includes two steps. The first step is to come up with initialization using the spectral method, which typically is done by computing the top singular vectors of some data constructed matrices. Now, because now our data yi can contain some entries that are arbitrarily perturbed, and therefore its top singular vectors can also become arbitrarily perturbed, and therefore we may not be able to guarantee a good initialization anymore. And this also holds true even when you use a mean truncation, such as use in truncated Worthington flow, because the mean value of your data, again, is not robust to arbitrary adversarial outliers. Similarly, when you perform local search using the gradient descent type of updates, because our search direction is a linear combination of the sample gradient, where each of the sample gradient depends on one data point. And now some of these search directions can also become arbitrarily perturbed, and therefore we cannot guarantee our search direction will be reliable. And in fact, this diagnosis implies that even with a single outlier, the algorithm can potentially fail to deliver useful estimates. Now, this diagnosis also implies a potential remedy to our problem. So the key idea here is maybe instead of using some quantities that are not robust to outliers, we may resort to robust statistics and borrow some of these robust statistics into our algorithm design. A particular quantity we are going to use is the sample median, which is known to be robust to adversarial outliers. And the key idea here is that we are going to discard samples adaptively based on how large the sample gradients or the sample values deviate from the sample median. And with understanding that samples that are excessively large may potentially correspond to outliers. Okay, so with this in mind, we propose the following robustification of the spectral initialization, where we are going to essentially initialize our low rank matrix factors using the top R singular vectors of a data matrix, which is constructed only using data samples whose absolute values is only a few times smaller than the sample median of the measurement values. Similarly, we are going to robustify our gradient descent update, where in every iteration, our search direction is only going to construct it using a subset of the samples, where the subset of the sample that we are going to select is based on the current measurement residue we have using the current estimates. And the idea is that we are going to only retain samples whose measurement residue is a small times smaller than the sample median of the measurement residues. So imagine that if you are getting close to the ground truth, and all your clean measurements will then essentially have a very small measurement residue, except on your outliers, the measurement residue will be large. So this truncation strategy will necessarily ensure that only the measurements that corresponds to clean samples will be retained, while samples that corresponds to the outliers will have a high probability of being discarded. And therefore, we can make the search direction more robust and corresponding to pointing to the direction of the ground truth that we are really interested in recovering. Okay, so with this in mind, with this, we now have this new algorithm that we call the median truncated gradient descent algorithm. And this algorithm, as you can see, structurally has a very similar structure as a vanilla gradient descent, so that you can essentially implement this algorithm with a minimum overhead in terms of computation on top of the vanilla gradient descent, but with the hope that being more robust to adversarial outliers. Okay. So this shows sort of a typical result for this type of median truncated gradient descent approach for the problem low rank matrix sensing, where we show that essentially with this algorithm, we can achieve again epsilon complexity with a number of order kappa log 1 over epsilon iterations, as long as the sample size is a little bit larger than the degrees of freedom of this low rank matrix sensing problem. But as a benefit that now we can also handle a fraction of outliers that is roughly on the order 1 over square root of R, where R is the rank of the matrix. So therefore, we essentially now have a new algorithm that become more robust to the vanilla gradient descent in an oblivious fashion. Before we continue, let's just look at this simple example on real data where we're running this low rank matrix sensing problem for this image recovery, where if we are running gradient descent without any outlier, we get the second image as a reconstruction result. However, even with 1% of outlier, gradient descent becomes highly sensitive and cannot produce any useful result. Nonetheless, if we now run this median truncated gradient descent algorithm for the same corrupted data, we can essentially get a reconstruction result that is as good, almost as good as the reconstruction result of gradient descent as if there are no outliers. Okay. Now, another possible way to deal with outliers, as also proposed by some recent work, is to actually use a different loss function that are more robust to outliers. So one candidate is to use this least absolute deviation loss, which simply replaces the L2 squared L2 loss by L1 loss. And with this new loss function, we have a non-smooth loss to deal with, and therefore we can no longer simply run gradient iteration, but has to result to subgradient iterations. And another important realization when we run subgradient algorithm is to realize that due to the maybe existence of outliers, we can no longer also use constant step size. But typically, the step size needs to follow some decay rule, such as using the polyak step size or geometrically decaying step sizes. Turns out that the earlier discussed scale gradient approach can also be applied to these non-smooth problems, where we can also apply the similar preconditioners to the subgradients, where we essentially can have the same set of algorithms where we don't need to change any of the other factors except adding these preconditioners. Now we can also get the similar type of convergence acceleration by using the scaled subgradient method, where we can remove the dependence with respect to the condition number kappa in the iteration complexity, so that now we essentially have a new algorithm that is not only robust to the EU conditioning of the underlying low rank matrices, but are also robust to adversarial corruptions in our measurement models. Another example that we would like to talk a little bit about in this tutorial is the application about the mixing sparse and low rank matrices. So suppose we are given a matrix M, which is a superposition of a low rank component L and a sparse component S. And the natural question is, can we still hope to recover this low rank matrix and the sparse component from only the mixture observation M? So this is a problem that typically is known in the literature called the robust PCA problem. And it has many applications in video surveillance, where you can think of essentially the low rank component as a background in the video and the sparse component as a foreground in the video that captures the moving objects and so on. So being able to separate the low rank component from the sparse component essentially give us the capability to do this separation of background and foreground in video surveillance applications. A standard, very natural non-convex approach to this problem is essentially try to do the similar thing as before, but now that we are going to do this matrix factorization on the low rank component, but we also has to be mindful about the non-zero sparse entries in the matrix S. So a typical assumption that we're going to impose on the sparse matrix is to enforce some sort of spreadness about its non-zero entries. Particularly, we are going to think about the non-zero entries as spread over both row-wise and column-wise, so that each row can contain normals and S fraction of outliers, and similarly, each column can contain normals and S fraction of outliers. Now, we're only going to constrain sort of the sparsity level of the outliers, but not going to make any assumption about its signs or its amplitudes. Okay, so with this in mind, a natural loss function isn't try to minimize this least square loss by looking for matrices, sparse matrices S that satisfies the spreadness patterns, and as well as the low rank matrix factors X and Y. Okay. Now, a natural thought is to modify our earlier gradient descent type approach, but now with an additional steps that we are going to also alternatively estimate the sparse component. Now, in terms of the spectral initialization, we are going to also modify it a little bit by first use the vanilla data matrix and just sort of scan out its large components as our initial estimate of the sparse corruption, and then use a sparse corruption subtracted data matrix as our candidate to perform the spectral method. And with this initialization, in the iterative updates, we can essentially just alternate between a hard thresholding step, which simply try to update our estimates of the sparse corruptions through this hard thresholding operation, which only sort of retains the large entries according to the spreadness patterns. And in the update of the low rank factors, we can in fact also use the same idea that instead of using the vanilla gradient, we're going to use this scaled gradient updates, where we are going to apply a similar preconditioning to these factors with the hope that the corresponding updates is more robust to U conditioning. So with this in place, we have the following theoretical guarantee, where essentially if we set the parameter gamma, which is used in estimating the sparse component as equal to 2, and as a step size roughly on the around some small constant, then as long as the fraction of outliers is upper bounded by this level on the order 1 over mu times r to the 3 to the 2th order times kappa, then this approach essentially will converge linearly to the low rank matrix in the stated rate on the slide. And particularly because we are taking a constant step size, this is essentially saying we can reach epsilon accuracy within a number iteration on the order log 1 over epsilon, which is again independent with respect to the condition number. In fact, for people who are sort of expert with this problem, we know that if we have adversarial outliers as in this model, the optimal fraction of outlier we can handle, for example, using a convex optimization approach, is actually on the order 1 over mu times r. So this result is actually a little bit suboptimal by a fraction of kappa times 1 over square root of r. It will be very interesting to see whether this gap can be closed in the future. Now, again, compare with the standard approach using just vanilla gradient descent, we see essentially this scale gradient descent based approach, again, strictly improve over the statistical guarantee of the vanilla gradient descent approach by allowing a larger fraction of outliers, as well as improving the convergence rate by a factor of the condition number kappa. To be fair, the paper by Ye on vanilla gradient descent also analyzed a case where we only have partial observations. Well, for the problem of scale gradient descent, it is still an open problem to carry out analysis for the partial observation setting for this non-convex RPCA problem. Okay, so with that, that covers our discussion about design and analysis of robust non-convex approaches that are provably robust to both EU conditioning and corruptions. Now we are finally getting close to the end of this tutorial. As some concluding remarks, the high-level key idea of this tutorial is to inject some statistical thinking when reasoning about the efficacy of optimization algorithms. Particularly, we see that even for some very challenging non-convex problems, with the help of statistical models, we can often instead argue about the average case performance of these algorithms, which can sometimes be very simple algorithms such as gradient descent, and come up with very efficient computation guarantees. So again, putting in one sentence, we know that when data are generated by certain statistical models, the problem can be much nicer than the worst case instances. There has been a growing list of benign non-convex optimization problems. Some of them we talk a little bit in this tutorial, but there are also many more problems that we don't have time to talk about, such as blind deconvolution, discrete learning, tensor completion, and so on. And there are tons of open problems. One of the problems that might be interesting is to characterize, for example, generic landscape properties that enable fast convergence of gradient methods from random initialization. So we've seen one example like this for the problem of phase retrieval. However, it is still quite challenging and open problem to rigorously justify the effectiveness of random initialization for a larger class of non-convex statistical estimation problems. Most of the theory we talk about in this tutorial often requires some sort of statistical assumptions, such as having Gaussian data, having a uniform observation pattern, which sometimes can be quite stringent and do not necessarily match with practice. And therefore, it is a very interesting open problem to think about how to relax these stringent assumptions underlying the data. Last but not least, it is also quite interesting to think about how to generalize the results that we've seen in this tutorial to the scenario where the data are distributed at different locations, and we need to have distributed optimization algorithms to do the statistical estimation. And most of these algorithms do not have a counterpart in terms of theory when we go to the distributed setting. Finally, it's also very interesting to identify new classes of non-convex problems that admit efficient optimization procedures. We have been trying really hard to put together some of the results we discussed in this tutorial in some readable overview and monographs in the last 2 years. So one of the paper we put together that has been published in Transactional Signal Processing as an overview article last year is on non-convex optimization for low-rank matrix factorization. Just very recently, we also have completed another monograph for foundations and trends in machine learning for spectral methods, particularly coming from a statistical perspective. So I encourage you to visit this overview and the tutorials if you find the materials in this tutorial interesting. With that, I would like to conclude with just a list of references. Because of time, we really don't have time to get into many of the very exciting new advances in this area, but we tried very hard to just compile this list of references, which is already very long, but still admittedly an incomplete list, so that if you're interested, you can go to these references to learn more about this topic. Okay? So with that, I will conclude, and thank you so much for your attention.